Thank you very much. It's great to be in Poland. Actually, this is my second time in Poland. I was here, actually not long after that picture, in 1986. I was here in Warsaw for the Olympiads. But I haven't been back since. It's been 30 years, so it's been good to be back in Poland. It's changed a little bit since then. Okay, but okay. So yes, I'll be talking about this work I did on this question of Erdős in discrepancy theory. So let me first talk a little bit about what discrepancy theory is. So it's a sort of a branch of combinatorics, I guess, and geometry. So it shows up. It's actually useful in practical applications in computer science. Although the particular problem of Erdős maybe is more of theoretical interest. But there are many problems in computer science where you want to solve a problem. You want to find some number or compute something, and it's hard to do exactly. So you maybe just want an approximate answer. And often one way to get an approximate answer is to use some sort of randomness. So a simple example is suppose you have some region inside a square. So this region is supposed to be inside a unit square, which I haven't drawn. But suppose you have some unit square, area 1, and you have some region inside the square, and you want to know what the area of this region is. A very basic mathematical question. Now, if you know the formula for the curve, maybe you can do some calculus, do some integration. But maybe you don't know the formula for the curve, or maybe the integral is just too hard to compute. But you still want to know the area, maybe not exactly, but maybe approximately. So there's a number of ways to try to compute the area. You can try to break up into little squares, for example, and count the squares. But there's one way which is fairly fast, which is called Monte Carlo integration. So what you can do is that, so now I've got the square here. You can just start selecting random dots inside the square. Like you can maybe imagine throwing darts at this square, and maybe there's 100 dots here, and some of the dots will be inside the region and some of the dots outside the region, and you just count what proportion of the dots lie inside the region, and that will be an estimate for the area. So maybe if you make 100 dots here and 60 of them lie inside this region, then you would guess that the area of this region is roughly 0.6. Okay, so that's a very simple strategy, and that's called the Monte Carlo method, because Monte Carlo is famous for its casinos. I think that's the reason why it's called that. And it works reasonably well, but it's not perfect, because one of the problems is that when you select dots randomly, they're not completely uniformly distributed. So you can see that with these random dots here, sometimes there's some clusters where there's quite a lot of dots, and then there's a lot of empty regions where there's not many dots. And so because of that, the estimate that you get may be a little bit off. Like here, there's actually quite a lot of dots, and so maybe you're overcounting the area here, but you're also undercounting the area here. And so the problem is that these dots are not very uniformly distributed. So you could ask, maybe instead of using random dots, you could maybe find some better set of dots to use to compute this area more accurately. So for example, you could try a grid. Okay, so that's another obvious thing to try. So a grid can work well in some cases, but grids also have their own problems. So maybe if I can just quickly draw a picture here. If you make a grid of points like this, and suppose you want to find the area of this region here, okay, then this region happens to miss all the points in the grid, and so you think the area is 0. So there's this big region, this big sort of rectangle here, where there's a large discrepancy between what the area of this region is and how many dots there are in this region. So this is not such a great choice either. So there's this sort of general question of what is a good set of points to pick, which sort of which has low discrepancy. That whenever you pick a nice region or space, the number of points in that space is roughly what it should be. And that general kind of question is what discrepancy theory is about, trying to construct things like sequences of points, sets of points, which are very well balanced in some sense. Okay, so this is a two-dimensional problem. You can also talk about three-dimensional, higher dimensional problems. The particular question of Erdős that we'll be talking about is actually a one-dimensional problem. So, so this picture was really just for illustration. There'll be no more two-dimensional pictures in this talk. It's all one-dimensional. So instead of thinking about points in a square, the discrepancy problem is actually about a one-dimensional sequence. So just a sequence of, say, plus and minus ones. Okay, so these are sometimes called sign patterns. So you look at sequences that are either plus 1, minus 1, plus 1, minus 1, say f of 1, f of 2, f of 3. And the general question is you want to find sequences that are as balanced as possible, have very low discrepancy. So if you pick a sequence like this randomly, like maybe you flip a coin for the first number, if it's heads plus 1, tails minus 1, and then you flip another coin and you keep flipping coins. You'd expect that over time, half the numbers will be plus 1, half the numbers will be minus 1. Okay? So, so if you pick if you pick, say, the first 7 terms in the sequence, about half of them should be plus 1, half of them minus 1. In fact, that's pretty much the case. You have 3 plus 1s and 4 minus 1s. Another way of saying that is that if you add up all the signs in some block like this, like if you add up all these signs, there are 7 signs here. So this sum could be anywhere between minus 7 and plus 7, but it's actually a lot smaller. There's a lot of cancellation. There's 3 plus 1s and 4 minus 1s. And so inside this block, the total sum is actually only minus 1. It's actually a lot smaller. So this sequence has pretty low discrepancy if you look just at this block of 7. But maybe if you look at a bigger block or some other, if you add up your sequence in some other way, maybe you will get bigger discrepancy. So the general problem here is how can you make a sequence with as low discrepancy as possible, like to make as many of these sums as small as you can. So this is sort of a general mathematical question motivated by these sort of applications. Okay, so depending on which sums you're trying to make small, this question is either very easy or very hard. So that's a very easy type of this question. So let's just look at partial sums. Okay, so if you have a sequence f1, f2, f3, f4, you can take what's called partial sums. You can just sum the first 2, first 3, first 4 terms in the sequence, and you can ask how small can you make all these sums? So can you make all these partial sums small at the same time? Now you can talk about infinite sequences or finite sequences. Let's talk about finite sequences. So let's say you have 100 signs. Right? You have 100 numbers plus or minus 1, and you just want to make all the partial sums small. Okay. So mathematically, what you're trying to do is you want to minimize this quantity. This is the largest size of the partial sums. That's what this formula is trying to say. So you could do this in a number of ways. You could just say, let's do it randomly, like the Monte Carlo method. You just flip coins, and you plus 1, minus 1, plus 1, plus 1, minus 1. You flip coins. And there's a standard computation in probability using something called the Chernoff inequality, which I won't talk about here. But it turns out that normally, if you just pick signs randomly, the partial sums can get reasonably big. It turns out that these sums will typically be of size about square root of n. So if you had, say, a million numbers and you add them all up, typically the sum is going to be of size about 1,000, plus or minus 1,000. Okay, it's related to something called the central limit theorem, if you know what that is. So that's not too bad. It's smaller than n, which is sort of the trivial thing, but it's not that great either. But in this particular case, you can do much better than a random sequence. So if you want all the partial sums to be small, the simplest thing to do is just have an alternating sequence: plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. Okay, because if you have an alternating sequence, then every partial sum is actually going to be either 0 or 1. Okay, so like this, the sum of the first 2 elements is 0, sum of the first 3 elements is 1, 0, 1, 0, 1. It never gets bigger than that. Okay, so you can make, if all you're interested in is partial sums of just the first m elements, it's very easy to make a very low discrepancy sequence. Okay, okay, so that's a very simple thing. And this is not very deep, but it's already useful. Like when you row in a rowboat, they always alternate back and forth, left, right, left, right, left, right. And roughly speaking, the reason you do that is because that's the pattern that has low discrepancy in this sense. Otherwise, you would be a lot less stable. Okay. All right, so this sequence of which is alternating like this, it has low discrepancy if you're only summing just in order, like all the numbers from 1 to m. But if you're summing in a different way, this sequence actually has a very high discrepancy. Like if you only sum the odd entry, every other element, like say the first element, third element, fifth element, seventh element, if you sum along an arithmetic progression, then suddenly there's a very big discrepancy because now you only see plus ones, you don't see minus ones. So this sequence will now have a very big discrepancy if you are summing over this progression here. So while this sequence is very balanced if you just sum in order, if you sum in a progression, you can get a very, it is actually quite bad. So you can ask, all right, so can you find another sequence which is balanced along every single arithmetic progression? So the mathematical question here is that can you find some sequence of signs, plus and minus ones, such that whenever you sum over any arithmetic progression, so this is an arithmetic progression a plus r up to a plus kr, or k minus 1r, that can you make all these sums small? So can you make, for example, f of 3 plus f of 13 plus f of 23 small, or f of 5 plus f of 7 plus f of 9 small? Can you make all these sums small at the same time? Okay. Now, again, you can try doing this randomly. If you have n signs and you pick them at random, you can do some probability, and you'll find that these sort of sums are of size about square root of n. That's what you get when you do things randomly. But can you do better? Can you beat the random example? So the alternating example, plus 1, minus 1, plus 1, minus 1, is now very bad. This sum can now be as big as like n over 2 or something. It can be quite large. So it turns out that you can do a bit better than square root of n, but not much. So first of all, there's actually a very nice theorem in combinatorics called van der Waals' theorem, proven in 1927. What this theorem says, it's a theorem about coloring. So here's the integers 1, 2, 3, 4, 5, 6, and so forth. And what the theorem says is that if you take all the numbers in the world and you color them into different colors, let's say blue and red, say 2 colors. Okay, so you color some colors blue and some colors red, then no matter how you color these numbers, somewhere inside one of the colors, there's going to be an arithmetic progression of any length you like. So here, for example, if you color these guys red and these guys blue, then here we have an arithmetic progression of length 3. The number 3, 6, and 9 is an arithmetic progression, and they're all red. Okay, so all the here we have a progression of length 3. If you change this color from red to blue, then you no longer have this length 3 red progression, but you will have instead created a length 3 blue progression down here. Okay, and in fact, no matter how you color these 9 numbers into 2 colors, you'll always find a length 3 progression. And as you get longer and longer, you'll find that you will have to have more and more longer progressions. So this is one of the first examples of a theorem in what's called Ramsey theory. Maybe the most famous example of a Ramsey theorem is that if you have 6 people in a room, then either 3 of them know each other or 3 of them don't know each other. Right? And it doesn't matter how you arrange it, who you invite, you always have either 3 friends or 3 strangers. Okay, so this is sort of a similar theorem in a similar spirit. You either get a red progression or a blue progression. Anyway, because of this theorem, this puts a limit on how low discrepancy you can have if you're summing over arithmetic progressions. Because if you have a sign pattern, plus and minus ones, you can think of a plus sign pattern as a way of coloring the integers. You can think of plus 1 as a color, like red, and minus 1 as a color, like blue. And, So what van der Waals' theorem tells you is that if you keep picking plus and minus ones, you'll be forced, no matter how you try to pick to make things as balanced as possible, eventually you'll find an arithmetic progression where everybody is plus 1 or everyone is minus 1, and then so you'll find a long progression where there's a lot of discrepancy. So you can't make the discrepancy bounded, it has to grow. Now how fast it was to grow is actually quite a tricky question. It was eventually worked out, so in 1964, Klaus Roth showed that, in fact, that this discrepancy, no matter how you pick your signs, you can do better than square root of n, but you can't do better than the fourth root of n, n to the 1/4. So it's a slightly surprising result. Actually, this was one of, maybe his third most famous theorem. He got the Fields Medal for many things, and this is maybe, well, not his most important theorem, but one of them. And then somewhat later on, Matuszek and Spencer showed that this is actually, you can't improve this. This is the best possible. That there are sequences of plus minus 1 whose discrepancy is about n to the 1/4. Okay. Okay, times a constant. Okay, so that's the answer if you take all progressions. Okay, so if you only want discrepancy along partial sums, then you can make the discrepancy bounded. If you're taking the discrepancy along all arithmetic progressions, the discrepancy grows, like n to the 1/4. And so the question of Erdős was sort of in between these two sort of extreme cases. So Erdős, who was actually motivated by some questions in number theory, we'll talk about that later, asked, suppose you want to measure discrepancy not along all arithmetic progressions, but only along what's called homogeneous arithmetic progressions. These are progressions which start at some a, and then they just add a to itself. So a, 2a, 3a, 4a. So for example, 10, 20, 30, 40 is a homogeneous arithmetic progression. And so suppose you're only interested in summing over these special progressions. Now can you make the discrepancy small? How small can you make the discrepancy of a sequence? How can you choose the signs to be as balanced as possible among these homogeneous progressions? So this may seem like a sort of a random question, but Erdős somehow had this knack. You know, he asked thousands of questions, but he tended to pick the ones that had really interesting solutions somehow. It's almost forced. I mean, and there's a reason for that. He didn't sort of create these questions randomly. You know, he wanted to know this because it would help with some other number theory question, which we'll talk about later. Okay, yeah. So So another way of saying it is that given any threshold c, can you make, like say c is 5, can you make sequences of signs which are really, really long, but where all the discrepancies along homogeneous progressions are at most 5? Okay, so like, can you make sequences that are really balanced along all these homogeneous progressions? Okay. Okay. So so you can ask when must the discrepancy be bigger than c for various c? And so one way to attack the problem is to start with very small values of c, where the question is easier, and then slowly go up. Okay. So for example, c equals 1 is the easiest. Okay. The moment you have even one sign, you immediately get a discrepancy of 1, because 1 is itself an arithmetic progression. So you know, the moment you place one number, you have to have a discrepancy of 1. Okay. So what about 2? Okay, so if you have a sequence of signs, must it be that the discrepancy has to be at least 2 along some progression? So not for a while, as it turns out. So here is an example of a sequence of 11 signs, and it turns out that this sequence never has discrepancy 2. The discrepancy is actually 1. So if I pick, for example, the third and sixth element, 3 and 6, these two elements sum to 0. If I pick the third, sixth, and ninth, that sums to -1. And okay, I'm not going to do all of them, but all these all the progressions here, if you sum the discrepancies, it's either -1, 0, or +1, never 2, never -2. So this sequence is very balanced along every single homogeneous progression, and it's fairly long, size 11, length 11. But it turns out that that's the longest, right? The moment you add one more term, if you take a sequence of length 12, you must have a discrepancy of size 2. And so maybe I'll actually prove this, because it's a fun, it's very much like solving a Sudoku puzzle. So this is a fun little proof. Yeah, so the claim is you take all the numbers from 1 to 12. Okay. And you're going to pick signs, +1, -1, +1, -1. And what I'm going to tell you is that no matter how you pick the signs, somewhere there must be a discrepancy of at least 2. Now, you could just check all the different patterns one by one, but there are 2 to the 12 of these. That's what, 4096? Okay, I'm not going to do that. The easiest way to prove this is to prove a contradiction. Okay, so assume the discrepancy is less than 2. Okay, so what that means is that every time I sum on a progression, homogeneous progression, the sum is never plus 2 or minus 2, it's only the minus 1, 0, or plus 1. These are the only sums that are allowed. Okay, and now I can actually see what happens. So the first term is either plus 1 or minus 1. Now it turns out that it doesn't really matter which one it is. Without loss of generality, it's going to be plus 1. If it's minus 1, I can flip all the signs. I can replace all the signs by their opposite, and it has the same discrepancy. So I'll assume that the first term is plus 1. Okay, so now I can solve for f of 2. Because if f of 2 is plus 1, then the progression 1 and 2 would have discrepancy 2. Plus 1 is 2. So it can't be plus 1 here. So it has to be minus 1. Okay. Now 3, I can't say anything just yet because 3, if it's plus 1 or minus 1, in either case, the sum of f1, f2, f3 is within the limits that we allowed. It's either plus or minus 1. So we can't do anything about 3, but we can do something about 4. Okay? Because 2 and 4 is a progression, homogeneous progression. And if you have minus 1 here, you can't have minus 1 here, because minus 1 is minus 2. That's not allowed. So this has to be plus 1. Okay? And then from 4, I can get 8, because 4 and 8 is also a homogeneous progression. So if 4 is plus 1, 8 can't be plus 1, it has to be minus 1. Okay, then you get stuck for a little bit, but now we can go back to 3. Now I can say something about 3. Because if 3 was plus 1, then the length 4 progression, see, minus 1 plus 1 plus 1 plus 1 is 2. And that's not allowed. So this can't be plus 1. This has to be minus 1. Okay. See, it's very much like solving a Sudoku puzzle. Right? You sort of, each cell you solve sort of helps you solve the other cells. Okay? Once you do 3, then 6. 3 and 6 is a progression. So minus 1, this has to be plus 1 to balance it out. Otherwise, minus 1 is minus 2. 6 gives you 12. This has to be minus 1, because otherwise plus 1 is 2. Let's see, what next? 5. I can now solve for 5, because if this was plus 1, minus 1, minus 1, plus 1, plus 1, plus 1 is too big. So it has to be minus 1. Once I have 5, I can do 10. Minus 1, this has to be plus 1. What else? 7 I can do. Let's see. Minus 1, minus 1, minus 1, 1, minus 1, 1. This has to be plus 1 to balance this minus 1. Otherwise, the whole sum is minus 2. Similarly, 9 has to be minus 1. Okay, well, you can just trust me. If it's plus 1, the whole thing would be plus 2. But at this point, I think I can declare victory because this progression, 3, 6, 9, 12, has to be minus 2. Sums to minus 2. Okay, so you can't actually solve this Sudoku puzzle. Okay, so right, so well, this is a cute little thing. All right, so that's 2. Okay, so that wasn't that hard. So maybe 3 is going to be just a little bit harder, like 50% harder. Unfortunately, it's not. This is an example of what's called a 2-sat problem in computer science. When you get to c equals 3, you have let's get a 3-sat problem, slightly harder. Right. So okay. So now you can ask. Okay. So this sequence has discrepancy 2. How long do you have to go before you have to have discrepancy 3? So this actually took quite a while to work out. So it wasn't until like 3 years ago, in 2014, 2 computer scientists, Konev and Lisitsa, answered this question. First of all, they found a sequence of length 1,160. There was 1,160 signs, plus or minus 1, such that no matter which homogeneous progression you pick, the discrepancy is always at most between minus 2 and plus 2. Never gets to plus 3, never gets to minus 3. Always minus 1, minus 2, minus 1, 0, 1, or 2. So that was already a bit surprising. But what's even more surprising is that that's the best possible. That if you add one more term, if you look at any sequence of size 1161, then no matter what you do, somewhere in that sequence there will be a progression where the sum is plus or minus 3. Okay, now this is something you can't do by checking all the cases. Okay, there's 2 to the 1161 sign patterns out there. So they had to use, so the problem is a type of computer science problem called a 3-sat problem. There's this, you get, so for example, like f1, f2, f3, they can't all be plus 1 because the discrepancy would be too big. And so there's lots of clauses like this, and so they built a custom-built 3-sat solver to do this. And they eventually showed this was, so they basically proved by computer. The computer proof at the time actually achieved the record of the world's longest proof for 2 years. The certificate that actually shows that 1160 is best possible. I think the file that actually verifies this is 13 gigabytes big. So I think in some of the media it was called a Wikipedia-sized proof, and it was the record for the biggest proof to appear in mathematics. That's no longer the case. There's actually another proof which is now 200 terabytes of something else, which is even bigger. But anyway, so the question was only answered in 2014. The answer is you need to be 1160. By the way, here's the sequence which has discrepancy 2. But anyway, all right. So okay, that's 3. Then maybe 4. Okay. So how long do you have to be until you have a sequence of discrepancy at least 4? So kind of Sitzer was able to find a fairly long sequence. They found a sequence of 13,900 signs, which have discrepancy at most 4. So discrepancy was always less than 4. So you can actually go for quite a while just sort of by a greedy algorithm. Like you just sort of lay down signs one at a time, and at every stage you look at all the progressions that come with that number in it, and you just choose the sign to somehow keep avoiding plus or minus 4. But eventually you get hemmed in, okay, and they got stuck around 13,900. So that's the longest sequence that we know of discrepancy 3. But we don't know if that's longer. Maybe there's a longer one. And in fact, until 2015, we didn't. That was the record. We did not know if the discrepancy would ever get to 4. Maybe the discrepancy would just stay at 3 forever. Okay. So so in 2015, I actually managed to solve this problem. That in fact, the discrepancy must grow. That no matter what threshold you pick, 4, 5, 10, whatever, eventually your discrepancy must get bigger than any number. Okay. So this is basically a combinatorics question. It's just it's like solving Sudoku. But actually, the solution comes outside of combinatorics. You have to use some number theory, in fact, even some probability theory and some information theory. Number theory was not too surprising because the reason Erdős was even interested in this question came from number theory to begin with. Is that going to be one of them? Okay. But I'll come to that later. Okay. So to get a handle on sort of where the enemy is, so you can ask, how do you build sequences that have small discrepancy? Okay, so how do you actually build nice long sequences of signs where all these sums are kind of small? Okay, so you could try choosing signs randomly, plus minus 1, you flip coins. That's not a very good choice. If you flip coins randomly, the discrepancy will be of size about root n. So for example, we had this example Konnev and Lisitsa of this sequence of 13,000 signs whose discrepancy is just 3. If you pick the signs randomly, the discrepancy would be more like 100. Okay, random is actually a very bad choice. You want a very non-random sequence. Okay, so the most dangerous sequences that for this problem are not the random sequences, but very, very special sequences that are somehow designed to have low discrepancy. Okay, so actually, it turns out that sort of a really good example of a sequence which is a real problem is a sequence from number theory called the Liouville function, lambda. So the Liouville function is a sign pattern. It gives you plus minus 1 and minus 1, and it's defined using prime numbers, which are my favorite mathematical object. So the way you define it is that lambda of a number n is plus 1 if n is the product of an even number of primes, and minus 1 if you're product of an odd number of primes. So it measures how many primes there are in your number. So lambda of 6, for example, 6 is 2 times 3, 2 primes, so that's even, that's a plus 1. But lambda of 30, that's 2 times 3 times 5, that's 3 primes, so that's minus 1. Okay? So it's a sequence of plus and minus 1s. And it looks kind of random. So maybe if I just want to briefly just draw what it looks like here, since I have this picture, I may as well show you what it looks like. Okay, so 2 is 1 prime, 2 primes, 1 prime, 2 primes, 1 prime, 3 primes, 2 primes, and 2 times 2 times 3 primes. Okay, so it's basically a random-looking sequence of plus and minus 1s. So what's so special about the sequence? So this sequence has the property that it's completely multiplicative. That if you take lambda of a product, n times m, it just factors into lambda n times lambda m. So for example, lambda of 10 is lambda of 2 times lambda of 5. Okay, and if you just think about it, it's so obvious why it's true. Like if n has an even number of prime factors and m has an odd number of prime factors, then n times m must have an odd number of prime factors, and so forth. So it has this property, functions with this property are called completely multiplicative. And the reason why that's relevant is that if you want to sum the Liouville function on a progression like a, 2a, 3a, 4a, you can use the complete multiplicativity and you can just factor out the lambda of a. And so this sum over progressions is actually just has the same magnitude. It's just either plus or minus this partial sum here. So all these different sums that you're trying to make small, they actually simplify to just the partial sums. Okay, so if you want to make this sequence have low discrepancy, you just need to make only just the partial sums small, and that's a much easier task. So you would expect that this sequence will have smaller discrepancy, maybe because there are fewer sums that you want to make small. Now, so Erdős knew this actually. So this sort of sum actually is well studied. Number theorists know a lot about these sort of sums. It turns out, so there's a whole long story which I'm not going to talk about today. But this Liouville function is connected to a very famous function in mathematics, the Riemann zeta function, and in particular to the zeros of the zeta function. And this sum actually oscillates in a certain way, and the way it oscillates is controlled by where the zeros of the zeta function are. And we care quite a bit about where the zeros of the zeta function are. The famous Riemann hypothesis tells you where they are, but we can't prove that. But one very simple thing we know about this function is that it has so we would like all the zeros of this function to lie on a certain line, called the critical line. We don't know that, but we know that at least one of the zeros does. Right? There's at least one zero on that line. And just from that information, we can say that this sum is actually about as big as, it must grow like root k on average. So, so this sum actually does grow, and it grows about as fast as the random sequence. So the Liouville function actually is no better than the random sequence, but only because we know something about the zeta function. Okay, so I think, oh, hang on. Okay, so I think it is in the wrong order. But here I have a graph. These are the partial sums of the Liouville functions. It's called the summitary Liouville function. Like if you, for example, at 5,000, you can sum the first 5,000 terms in the sequence, and you get something about like minus 70 or so. And the size of this is roughly about the square root of the number. So it grows, but like the square root. And it also oscillates. And all these waves going up and down, these oscillations come from some zeros of the zeta function, as it turns out. Okay. So okay, for some reason that's out of order. Okay. So, okay, so this sequence is no good. Maybe I'll skip. Oh, okay, no. So there's another sequence which is a lot better, and it almost works, except for, so there's almost a counterexample to this conjecture of Erdős coming from these called Dirichlet characters. So these are another type of function that number theorists care about. These are functions that are also completely multiplicative, but now also periodic. So a good example is the function chi3. This is the function which is plus 1 if you are 1 modulo 3, minus 1 if you're 2 modulo 3, and 0 if you're 0 modulo 3. So it's if I can run this table again. So it's periodic, it keeps repeating itself. Okay? And because it's periodic, the partial sums never get bigger than 1, actually. They always just oscillate 1, 0, 1, 1, 0, 1, 1, 0, and so forth. Okay, no, 1, 0, 0, 1, 0, 0, and so forth. And so the partial sums are all bounded, and it's still completely multiplicative. So in fact, along any arithmetic progression, these sums are bounded. In fact, the discrepancy is always at most 1. So this is actually a very low discrepancy sequence, but it doesn't contradict the discrepancy problem because there are some zeros in it. You're not allowed to use zeros. So in the original problem, you're only allowed to use plus 1s and minus 1s. But if you're allowed to have some zeros, so this sequence is only 2/3 plus or minus 1, but the discrepancy is bounded. And you can make similar examples where, like say 99% of the numbers are plus or minus 1, the rest are zeros, but still the discrepancy is bounded. So this is part of what makes the problem hard, that there are these almost counterexamples to the problem. That the worst enemy is likely to be something that looks like this. Like maybe there's some way to fill in these zeros, replace them by some signs, and you can maybe modify this example to give you a very low discrepancy sequence. In fact, you can actually. But maybe I'll skip this slide, but there's a way to fill in the numbers here to make these numbers plus or minus 1 in such a way that the discrepancy only grows like log n. That, that if you have a big long sequence of length n, you can make a sequence using this sort of construction where the discrepancy is only about log n. And that's sort of consistent with what you see in these numerical examples. You have 1,160 numbers and the discrepancy only 2, 13,000 elements, the discrepancy only 3. That suggests logarithmic type growth. So the discrepancy only goes very, very slowly. It's part of what makes the question hard. Okay. So the first people to really seriously attack this question, this discrepancy question, and make some real progress was actually happened in 2010 when Timothy Gowers, a friend of mine actually, another Fields medalist, he actually organized what's called a polymath project. So it's an interesting experiment in mathematics. So rather than just get 1 or 2 people to work on a problem, they try to crowdsource the problem and get, so he opened up his blog to, there were dozens of people all over the world, so contributing ideas, doing all kinds of numerical experiments, trying all kinds of crazy things to solve this question. And they worked on it for about 2 or 3 years. And you can still see online, you can still see all the blogs and wikis and stuff and computer code and stuff that they did. It was the 5th project that was organized. It was called Polymath 5. So they didn't quite solve the question. And actually, there's a good reason for it. They were missing a key breakthrough, which only happened in 2015. But they did reduce the question. So I told you that multiplicative functions are going to be the most dangerous. And in fact, this is what they actually showed. Roughly speaking, what they showed is that rather than check all the different sign patterns in the world, you only really need to check the multiplicative. You only need to check the sequences that are multiplicative. And if you can do that, it turns out, roughly speaking, actually lying a little bit, you can then solve the entire problem. So things like the Dirichlet characters, the Loover function, these are actually the only things you need to understand. That if you have a multiplicative function, if you can show just for the multiplicative functions that the discrepancy is unbounded, which is the same thing as saying that the partial sums are unbounded in that case, then you can basically solve the whole problem. That's not completely true. You actually need to prove something slightly stronger than this to get back to the original discrepancy problem. But this was a big simplification. So, because there are a lot fewer multiplicative functions in the world than general functions. There's a lot more structure you can use. Okay, so I won't say how they did that. They used Fourier analysis, which apparently there was actually a talk on this earlier today. But that's, I think, in the interest of time, I'm going to skip over how they did that. So basically, the enemy is things like the Loover function. And so actually, a good model question is to actually just understand, go back to the Loover function. Now, we already know, because of the zeta function theory, that these partial sums are unbounded. But is there another way to prove, just for the Loover function, is there another way to show that the Loover function has unbounded partial sums? If you can do that, not using the zeta function, which is a trick which only works for the Liouville function, doesn't work for anything else, then you have a better chance of proving the general case. So it's often very useful in mathematics to reprove something that you already know how to do, but prove it in a different way. That often is a very fruitful thing to do. Okay, so here's the picture again. Yeah, so why does this sum go off to infinity? Why can't it stay sort of bounded? Okay, so we don't know as much about the Liouville function as we'd like to. It is a somewhat mysterious function. It's connected to the Riemann hypothesis. But there are some things you can do. Here's a fun little theorem about the Liouville function that you can actually prove in 5 lines. So for example, I can prove that the Liouville function has a lot of consecutive pairs where the signs are the same. So you can find infinitely many numbers where the consecutive values of the Liouville function are the same. So maybe if I go back to this board again. Sorry, keep turning lights on and off. All right. So this is the Liouville function. Plus 1, minus 1, minus 1, plus 1, minus 1, plus 1, minus 1, minus 1, so forth, plus 1. Okay, so you see there are lots of pairs where the sign is the same. Okay, that lambda of 8 is the same as lambda of 7, lambda of 10 is the same as lambda of 9. And it's not hard to show that this actually has to happen quite often, that there are that you must always have a lot of pairs like this. So this is another one of these Sudoku things where you prove by contradiction. So if this wasn't the case, if you didn't have very many of these same sign patterns, then what that would mean is that you would have to have a lot of alternating signs. That very often, whenever you go from n to n plus 1, the Liouville function has to change sign. Okay. But because the Liouville function is multiplicative, lambda of 2n has to be the negative of lambda of n, and lambda of 2n plus 2 has to be the negative of lambda of 2n plus 1. So if lambda of n and lambda of, if n and n plus 1 have the opposite sign, say plus and minus, then 2n and 2n plus 2 would also have to have the opposite sign, because this guy has to be the negative of this, and this guy has to be the negative of this. But then, because of the pigeonhole principle, no matter what sign you put in the middle, the sign in the middle either has to equal the sign on the right or the sign on the left. Okay, so you can use a very simple combinatorial tool, the pigeonhole principle, to find out that somewhere you can get the sign the same. Okay, so by playing sort of these Sudoku type games, so that's a very simple Sudoku puzzle, you can get somewhere. So in fact, this shows, if you actually work it out, this argument shows that you must actually get this equal sign about at least 1/3 of the time. There's an opposite question, like how often do you get must you have a sign change? Must you get an opposite sign? And that was actually a much harder question. So this simple Sudoku argument I gave you for showing that there's equal signs doesn't work for odd signs and for opposite signs. And that only was actually proved in 2015 by this great work of Matomaki and Madzuo. Actually, Maxim Madzuo was actually raised in Poland, actually, so he's a Polish mathematician. Well, he's in Canada now. But anyway, so these two number theorists did some very deep number theory, which I won't talk about here, that also controlled other sorts of sign patterns, and so now we know that the Liouville function either it stays the same sign infinitely often, and it also changes sign infinitely often. Now that's not by itself enough to show that the partial sums are unbounded, but you can keep sort of playing these Sudoku games and making them more and more complicated. In fact, actually, the reason I got into this was that I was working on a different project, actually with Kaisa Matomaki and Maxim Madzuo, on a different question in number theory. And that question was also about sign patterns of Liouville function. And I mentioned in my blog that it really felt like solving a Sudoku puzzle, what we were doing. And then someone commented on my blog, I worked on this Polymath 5 project a few years ago, and what we were doing also felt a lot like solving a Sudoku puzzle. And so maybe the two things are connected. And so because of that blog comment, I got interested in this discrepancy question. So it was, yeah, this is sort of one of the great benefits of doing everything online on the internet. You get all these sort of random by chance connections, which you wouldn't see if you're just working by yourself. Anyway, so you can keep doing more and more of these things, but this it gets way too technical to talk about in this sort of talk. But what you can find, to cut a somewhat long story short, is that you can find more and more properties of the Liouville function, which will eventually force the partial sums to become unbounded, unless there is a very strong bias inside the Liouville function. Now, what bias means is a bit complicated, but for example, you can take these sign matches. Okay, so we know that this sort of pattern occurs infinitely often, but we don't know where it occurs. We don't know for which n we have this equality, and maybe it's the places where this equation is true is actually very biased. Maybe it occurs a lot if your number n ends in 7 in base 10, but it doesn't occur much at all if your number n occurs in base 3. So that's kind of weird. That probably is not true, but that's an example of a bias that the truth or falsity of the statement might somehow be correlated with the last digit of your number, or maybe the residue class mod 13, or something weird like that. Now, so that's kind of weird, but that shouldn't happen. And if it doesn't happen, then by using this deep theory of Matamaki and Radziwiłł, we can actually then show that this partial sum is unbounded. So the only case where things go really wrong is when these sort of sums are really biased with respect to some residue, some congruence class, like the last digit 7. Now, the way you actually make that precise is that you actually have to use information theory, and there's this great concept from Shannon's information theory called mutual information. And basically, you need a lot of mutual information between this statement and the last digit of n. These two variables have to be very highly correlated in the sense of large mutual information, but that's a technicality. So if there's a conspiracy like that, then you run into a problem. But what you can show is that, the thing about conspiracies is that it's very hard to disprove a conspiracy. It could be that these primes really don't like numbers that end in 7, you know, or something, that equation. That there really could be some strong bias with respect to residue classes mod 10 or mod 13 or so forth. But what you can do is that you can use one conspiracy to fight another conspiracy. That it turns out that if the Liouville function had a lot of bias with respect to, say, the residue class mod 10, then it can't have that much bias with respect to the residue class mod 13, because that's sort of an independent sort of statistic. Or maybe it could, but if it's biased with both 10 and 13, it can't be biased with respect to mod 17 or something. And so what you can do is that you can start testing how correlated the Liouville function is, or the sign patterns are, with different congruence classes. And you can use this something called the Shannon entropy inequalities, and a lot of other tools in probability, which I won't talk about here. And eventually you can show that no matter how you arrange your sign pattern, there must be some set of residue classes where there isn't much correlation, that there isn't much bias. And so there are some good residue classes where you don't have this problem of having this conspiracy. And then you work with those primes, and then for those primes you use this theory of Matamaki and Radziwiłł, which I'm not talking about. And then you can actually solve the problem and prove these partial sums are unbounded. And that turns out to basically solve the question for multiplicative functions, and then you combine it with the work of this Polymath 5 project, and that solves the full problem. So that's skipping over all the details, unfortunately. That would be a separate hour talk to talk about these things. But I think that's a good place to stop, I think. So thank you very much.